We are now looking at the discriminant of a quadratic equation. Let's say our equation is f of x equals 0 for the function f of x given by ax squared plus bx plus c, and we need to require that a is different from 0. Well, if we want to solve our equation, we may want to apply the quadratic formula. So we'll be saying that x has to be the same as negative b plus minus, and then we have a square root inside. It has b squared minus 4ac, and all of that has to be divided by 2a. When we do this, we could be in the case that we have no solutions, so no zeros. We could have two distinct real zeros, or we could have only one real zero. And that's given by what's happening inside the square root. So what happens when we find the value of b squared minus 4ac? This is what we call the discriminant, and we denote with the Greek letter capital delta. This is our discriminant. And well, there will be three options for the value of the discriminant. It could be greater than 0. In this case, we say that there are two distinct real roots. So we can go ahead and solve what is the result of applying the square root, and then we have this plus minus that is going to give us the two distinct real roots. So let's write here two distinct real roots. Could be that the discriminant takes a value exactly 0. In that case, well, we're going to have a square root of 0, which is 0. So we're going to have only one value for the root, which is going to be minus b divided by 2a. So in this case, we say 1 real 0. Or it could happen that the value is less than 0. And then we cannot find in the real numbers what the result of applying the square root is. And we say that in this case there are no real zeros. Sorry, let me correct here. I say roots. We are talking about the equation, so we shouldn't say zeros. So in that case, we are two different real zeros. So the moral of this is that we can, if we can find the discriminant without solving the whole equation, we can decide in which one of the three situations we are, and that's what we're going to do in the next example. In this example, we have a quadratic equation with a parameter k. The equation is 4x squared plus 4 times k times x plus 9 equals to 0, and we want to decide for which values of x we are in the different cases. For the zeros, we have only one, or we have two distinct real zeros, or we have no real zeros. So the first thing that we are going to do is to find what is the value of the discriminant in this case. So for b squared, we have 4k, all of that squared, minus 4 times the coefficient of x squared, that's 4, times the coefficient of the independent term, well, that's 9. So let me take 4 squared as common factor to make my computations easier. We're going to have 4 squared times k squared minus 9. In the first case, we want to know when we have one real zero, so that means we want the discriminant to be equal to 0. So we want this 16 times k squared minus 9 to be equal to 0, which means that we want k squared to be equal to 9. So there are two options. Either k is the value 3, or k could be the value negative 3. For part B, we want now our discriminant to be positive. So the 16 doesn't matter for the positive part. We want k squared minus 9 to be greater than 0. You can think this as a quadratic in k, and then it's going to look like this. We have the value negative 3 as one of the x-intercepts, and the value 3 as the other intercept. If you look at k squared minus 9 as a function, quadratic function of k, and we want it to be positive. So that's going to happen when k is less than negative 3, or when k is greater than 3. And for the last case, the values we have left the discriminant will be less than 0 when k squared minus 9 is negative, which means that we want our value of k to be between -3 and 3. So we have the values of k that will make each of the three cases happen.